Welcome to my talk. My name is Chen Yang from the King Abdullah University of Science and Technology. The topic of my presentation is efficient locality-sensitive hashing over high-dimensional data streams. I have divided my talk into 5 parts. Approximate nearest neighbor search in high-dimensional space is a fundamental task in many applications, such as multimedia databases and recommender systems. In these applications, data objects are characterized as feature vectors and represented as points in a multi-dimensional space. Here we consider the problem of ANN search over data streams. Streaming data is data that is continuously generated by different sources. Solving the ANN search over data streams should make a good trade-off between update efficiency, search efficiency, and result qualities. Locality-sensitive hashing is a widely used solution to the ANN problem, as it has precise theoretical guarantees and empirical performance. According to the manner of generating hash functions, existing studies can be broadly classified into data-dependent methods and data-independent methods. The data-dependent method uses training data to learn hash functions that can capture the data density patterns. However, data distributions might change over time when dealing with streaming data, and the query accuracy will degrade if the hash functions have not been adapted. On the other hand, it's a lot harder to train the hash functions because it requires an expensive learning process. The data-independent methods rely on random projections to construct distance-preserving hash functions. Existing work can be classified as follows. The first one is multi-probe strategy. The second one is using P-tree to store each LSH function. And the third one is to project objects into low-dimensional space. However, all of them have some disadvantages. We propose a novel index called PDA-LSH. We adopt the LSM tree with cascading update technique for efficient updates. Then different from previous studies that apply kernel tail bounds to derive the number of LSH projections, we use a cumulative distribution function to estimate it more accurately. To improve the search performance, we propose to combine collision number and precise projection distance to select the candidates more effectively. Now, we first introduce the indexing method. We propose to use query-aware LSH functions to enjoy the benefit of multi-threaded search and query-aware bucket partitions. The indexing procedure projects each object along random lines and stores the projected values in separate indexes. For efficient updates, we use LSM trees to amortize I cost over multiple updates. Our search method combines both collision number and precise projection distance to select candidates. Given pre-specified thresholds, if a data object collides with a query object and at least L functions, and the square sum of the projection distances is at most t, that is a good candidate. Given a query object, we first compute its hash projections. Next, we expand the bucket boundary dynamically by checking objects in ascending order of their projection distances to the query object. In the first iteration, object 1 is checked and the radius updated. We also collect the collision number and the projection distance. In the second iteration, object 1 and 2 are checked. The collision number of object 1 is larger than the collision threshold. However, the projection distance doesn't meet the distance threshold constraint. In the third iteration, object 2 is checked and the radius is updated. In this case, object 1 can be selected as a candidate. Then we check the equilibrium distance between object 1 and Q. Now we introduce a parameter setting procedure. Previous study has shown that if objects are accessed in ascending order in of their projection distances, the correctness of the ANN is guaranteed if the algorithm has guarantees on the RCN problem. Next, we only consider the RCN problem. We use event 1 to denote that the collision number exceeds the collision threshold and the radius r. We use event 2 to denote that the projection distance is smaller than the distance threshold. The goal of our parameter setting is to provide upper bounds of false negative probability and false positive probability. However, event 1 and event 2 are not independent events. There exist some dependencies between them. Based on Bayes' theorem, we have this equation. The probability of event 1 can be computed, while there is no closed-form expression for the conditional probability. We resort to a heuristic and practical method. Our method consists of two steps. The first step is to set the number of LSH functions properly, so that we have enough projection information to make a distinction between near objects and far objects. We quantize the projection distances into collection number to enjoy a closed-form expression of the probability analysis. Obviously, given the search radius and two objects, their collision number follows the binomial distribution. The probability of two objects colliding more than a given threshold is exactly the right-tail probability of a binomial distribution. We propose to approximate the binomial distribution by the normal distribution and use its cumulative distribution function to estimate the right-tail probability. Now we aim to find the correct values of M and L such that the false positive and false negative probability are bounded. Based on the two inequations, we can derive a minimized number of LSH functions. Once the number of LSH functions is determined, our second step is to choose a correct set of thresholds where the collision threshold L is minimized. The smaller the collision threshold is, the earlier the candidates can be found, and the less index access cost is required. However, given specific thresholds, it's rather harder to compute the probability of both event 1 and event 2 holds, because it consists of conditional probability that has no closed-form expression. We use the Monte Carlo method to estimate it. We first randomly sample n points on a sphere with radius s. Then we find points that meet the constraints imposed by thresholds L and T. By the law of large numbers, the real probability can be approximated if n is large enough. Now let's turn to the experiment. We use two real-world datasets in our experiment. We compare our method with two state-of-the-art methods. We can see that our method has 3 times less space consumption than PDA-LSH. There are two reasons. One is that our method uses fewer indexes, as our CDF-based method derives a more accurate number of required LSH functions. Another reason is that the LSM tree is more space efficient than the B tree when handling updates, because it has no splitter and merging operations. For update efficiency, we can see that our method is more than 10 times faster than other methods. For the search performance, we can see that the IO cost of our method is much less than PDA-LSH, while offering comparable result accuracy. SRS has the smallest IO cost due to its small index size. However, this is often at the expense of sacrificing result accuracy. Further, it cannot scale to more than 6 projections, which means that it cannot achieve high result accuracy. Let's end with a conclusion. We propose a lower index called PDA-LSH. To improve the updated performance, we propose to use the right-flanked LSM trees to index each LSH projection. Then we propose a CDF-based method to derive a small number of required LSH functions. To improve the search performance, we combine both collision number and precise projection distance to select the candidates. Finally, we perform experiments to show the superiority of our method. Okay, that's all. Thank you for listening.